Welcome back. We're going to move on in chapter 15. We're going to talk about Carbenes. Carbenes are an interesting species. Let's use something that's interesting for them. Carbenes. Here we have a carbene. And how do you make this carbene? It's a fairly simple process. This is trichloromethane, better known as chloroform. Chloroform has a pKa of 7 here. You don't have to memorize that. Why would it be such a low number, you ask? Since it's a sp3 carbon with an H, normally your prediction would be 50 for that. Well, if you had to come up with an answer, you would probably talk to me about inductive effects. And the inductive effect would be stabilizing this carbon anion, which is usually a very unstable species. And because the chlorines are electronegative, they pull electrons towards the carbon's nucleus and stabilize the minus charge. And that's happening with all 3 chlorines. So pKa 7 makes it easily accessible with a cheap, strong base like hydroxide. Acid-base chemistry makes the conjugate base of chloroform. And what happens to this is that some of the chloroform, and I should point out it's some of, it's more like an equilibrium that goes like that. You get a little bit of this dichlorocarbene. Now, why would that happen to create a carbon that clearly has an octet violation? You do not see that very often. There would have to be something that helps stabilize that species. Well, you can argue that an anion of carbon is unstable. So by making it neutral, that helped it a little bit. And chloride is a stable species unto itself. So that's not unreasonable to see it leaving. We've seen that many times. So we get a little bit of dichlorocarbene, even though it has an octet violation. Dichlorocarbene and other carbenes have a very unique, for lack of a better word, I'm going to call it personality, in that they get attacked by electrons, in this case, the pi electrons of an alkene. And then after they get attacked, they have a lone pair which acts like a nucleophile. So the question is, why is this lone pair coming back to that carbon? You could hit pause on your video and think about that now. And the reason is, if you had to make one of these carbons into a carbocation, you would choose the bottom one because it's tertiary. The top one is secondary, less stable carbocation. Bottom carbon spends more time with a positive charge. So even though in this mechanism we don't see a charge on carbon ever, one of the arrows has to get the game going, and it's the first arrow. Where does that put its electrons? Well, if we take a look at the Lewis structure with actual empty p orbital here, the empty p orbital is a location for electrons. So that's where the electrons are going, into this empty p orbital. And the lone pair is living in a hybrid, an sp2 hybrid. You got 2 sigma bonds and a lone pair. I know we're going way back for this review. You count sigma bonds and lone pairs for hybridization, and it has 2 sigma bonds and 1 lone pair. That's sp2. So we got sp2 for the sigma and an empty p. So this thing's personality, it acts like an electrophile with its empty p orbital, and as a nucleophile after it acts like an electrophile with its lone pair. It's got dual personality. And in the end, you get a cyclopropane. This one has 2 halogens on it, often not desirable as a synthetic target, but this reaction has a fairly decent yield. So it is a good way to make a cyclopropane. We have never made cyclopropane before. And Carbenes, from now on, when you think about cyclopropane, this should be the first word that comes to your mind. Carbenes. And there are chemists who have developed methods of getting rid of the chlorines and replacing them with halogens, hydrogens, sorry, they are halogens, replacing them with hydrogens. We won't get into that, but those methods are out there. And let's look at stereochemistry before we do our own example down here. This trans double bond, recall that if you're going to make the 2 bonds at the same time, like the mechanism shows here, they both have to be on the same side of the molecule. Here I have it coming from on top. And that means the groups methyl and ethyl, which started trans to each other, will end trans to each other. There's no backside attack in this mechanism. So what we say is the geometry of the alkene is maintained. Trans begets trans. We had a trans alkene, and we have a trans product here with methyl on a wedge and ethyl on a dash. If I started with a cis alkene, like I did in the mechanism example, it ends up being cis here as well. We have the methyl cis to the ethyl, and here the methyl is still cis to the ethyl. All because it's a synchronous reaction. Happens at the same time. So we'll do our own example here. In fact, we could review even further backwards. Start with methane. And this would be 1 mole Cl2, and you make HCl. I don't like the way I made that happen. First mole Cl2, and you make HCl. And then you continue the reaction, Cl2, and we can do second mole, and third mole. And this is how these common methyl chlorides are made. And do it again, Cl2. Probably would have been better to show this side product. And we're going to make chloroform. And you guessed correctly, you're going to get Cl attached to CH3. Oh, pen stopped. I keep hitting the button with my hand. There we go. And you're wondering where we saw these and what the mechanism looked like. There's dichloromethane. My lab students, some of them would point out this is called dichloromethane. Dichloromethane, and its alternate name, methylene chloride. Oh, doesn't want to move. There we go. And chloroform has 3 chlorines and CH. And it's called chloroform. So when they want to make these are all useful molecules. What they do is they take a whole pile of methane and a lot of chlorine, and they just react it for a certain amount of time, and you get a mixture of all 3 of these. And all the reagents are so cheap that you can take a 20% yield and get significant amounts of each one and use for different things. You can do Sn2 reactions with chloromethane. Dichloromethane is a great solvent for a lot of things. And chloroform is another good solvent and reagent for making dichlorocarbene. So you take your Cl3CH and you react it with, say, step 1, NaOH, and step 2, let's do this one here. And put a big box here. Okay. And what's going to go in our big box? Let's run down what happens, all the steps. First step, sodium hydroxide reacts with chloroform to make the conjugate base. And that conjugate base undergoes, I guess you would just say, leaving group leaves, leaving behind a carbene. That's a carbene. When you hear carbenes, you think cyclopropane. What do you have to react a carbene with to make a cyclopropane? An alkene. And the propyl group here is cis to the ethyl and trans to the isopropyl. That better be the same in your product. However you want to show it is fine as long as it's clear. I'll show you my way. We can just go wedge for the groups that are on the same side and don't show anything else and you're fine. But don't forget to put dichlorocarbene up there. C with 2 CLs. You can draw them if you want. Use CCl2 if you want. And that's all you need to know about that carbene. And now we're going to look at some other carbenes, some that give us the more useful cyclopropane without any halogens on it, but very low yields. And then we'll show a slight improvement on that. And this is our last thing in chapter 15 before our next break. And here it is. We're going to make methylene carbene from diazomethane. I believe this is our first time we've seen diazomethane. I do want to point out you're going to see it again in chapter 18, maybe 17 and 18. I can't promise, but it's there. And diazomethane in this chapter is going to do what it's going to make a carbene. The yield of this carbene, though, is usually typically very low. I have yet to see one of these reactions go in excess of 40% yield. Diazomethane's name implies we have 2 azos. So a little heads up for your future. If you see azo in any name, there's nitrogen. And this has 2 nitrogens, so 2 nitrogens on methane. The 2 forms of the Lewis structure are here, and seeing as we're constantly reviewing, if you had to evaluate which structure was more stable than the other, you would definitely prefer a structure with a minus on a more electronegative nitrogen than a structure with a minus on a less electronegative carbon. So just to emphasize that point, yeah, it's not equilibrium, it's resonance, right? Resonance that favors the reactant. But that does not matter if we get this thing to react in this resonance form, then, you know, it's always resonating. And it's a little like Le Chatelet, except this is not an equilibrium. When this happens, it's removed from the equilibrium. You need to make more, but let's just say it. When this happens and then this leaves, it's removing it from resonance, which means you're going to have to make more. And not a hard mechanism. Why does this happen at all? Once again, you're creating an octet violation. You're saying, wow, that's not normal. It shouldn't happen. Well, what kind of a molecule is N2? It's a gas. This reaction is driven by what force? You hit pause. You're going to come back. You're going to be hit with the word entropy. Yes, entropy drives this reaction. Once nitrogen's gone, it's gone forever. It's a gas. And you have methylene carbene. Carbines do the same thing all chapter. They react with alkenes to make what? They make cyclopropane. In this case, it is exactly that. It's cyclopropane over here. Little quick review of nomenclature. That would be 1-methyl bicyclo. We've got a 3-carbon bridge to the left, a 1-carbon bridge to the right, and a 0-carbon bridge. There's no carbons in between, up and down. 3 + 1 + 2 is hexane. And that would be the name of our final cyclopropane product. Right there. So I don't think that mechanism needs to be redone. It's always the same mechanism. Once again, the pi puts its electrons in an empty p orbital here. You don't have to draw the p orbital. When you make a bond to an atom, it's got to go in some kind of orbital. And the lone pair is now a nucleophile. Why does it come to this carbon and not the top carbon? The bottom carbon spends more time with a plus charge because of hyperconjugation. I hope I'm starting to sound like a broken record. Okay, so making cyclopropanes. Yield always less than 40%. And put a little bit of a sad blue face here. Okay. If you want a higher yield for the same product, you do a little more work in this one. You can buy a zinc, actually typically you make a zinc copper couple. You fuse metallic zinc on a finely divided copper. You don't have to worry about the method of doing that. It's really an alloy. Do you remember those alloys? A mixture of two metals. And that is a redox alloy that will insert itself in between one of the carbon iodine bonds in diiodomethane. We have a very limited scope here. They have to be iodines. It doesn't work very well with the other halogens. You don't have to know the mechanism because it's not well known. But you see that the zinc ended up between the copper and the iodine, and the other iodine ended up on the carbon. So if you look carefully at this, it's called a carbenoid. And you know I like words and breaking them down. Carbenoid. Oid is the same as saying ish or like. So it behaves like a carbene, even though it's not a carbene. And why? Well, quite simply, we have a carbon attached to a halogen, which makes that an electrophile. So instead of having an empty p orbital, it has a leaving group. So if something attacked it, the leaving group would just leave. That's like a Sn2. And it's also got a carbon attached to a metal. Zinc is a metal. Those are anionic carbons attached to metal. So it behaves like a nucleophile there. And you see it in the mechanism. The carbon with the iodine is being attacked by the pi electrons, and the iodide's leaving, like an Sn2 reaction. After that happens, the carbon still has an anionic nature because of its bond to the metal. And that comes back to which carbon? The old broken record is scratching around again. And we're attacking the more substituted carbon. So over here, I'm just showing you how it behaves like a carbene. There's a real carbene. If you had the leaving group leave and the lone pair end up on the carbon, it is a carbene. And it's behaving like a carbene. We call it a carbenoid. And that brings to a close chapter 15. It's a short chapter. I mailed you chapter 16 at I believe the end of last week. So we will be starting up with that on the other side of our break. Looks like another 5-segment day. And I will see you in 5 minutes.